In the previous lecture, we worked out basically the dissipation of the electric and magnetic field, electromagnetic wave, when it is incident on a conductor. So just to review, when the electromagnetic wave hits the conductor, the free charges are allowed to move, but those free charges will naturally dissipate into the conductor, and so eventually the free charge will neutralize. There won't be a free charge anymore over a certain period of time, but then that electromagnetic wave, as it propagates through the conductor, can't get too far. It also will eventually dissipate into the conductor. And so what we have is basically these damped field equations, where you have the oscillating part right here, and then you have the dampening part right here. Okay. So now what I want to do is kind of define a few things, like something called the skin depth, which is essentially how deep can that electromagnetic wave penetrate into the conductor before it just dissipates to zero, basically grounds itself out. So this is the distance to reduce the amplitude. Distance to reduce the amplitude by 1 over E. Basically one, which is one constant, which is essentially the number 1/3. It's 1 over E. So the skin depth, which we'll call D, we can calculate as 1 over kappa. So you can kind of think of it like the spatial equivalent to a time constant. So K, the real part, determines the wavelength, lambda, because lambda is 2 pi over the wave number. The speed, if you remember, is omega divided by k. And the index of refraction, we said, was c times, or c divided by the speed, which is c k over omega, which is basically c over, which is what we're trying to remember. Okay. So Maxwell's equations, if we take a look, if we were to go back and take a look at Maxwell's equations, right? So the first and the third, the first and the second, so the first two of Maxwell's equations still say that our wave is transverse. So even though the wave now goes into this conductor, it is still a transverse wave. There's still a direction to the propagation, and the electric and magnetic fields should be perpendicular to that propagation vector, which you can think of like as the velocity. So if we assume that the polarization is in the x direction, so the electric field is some initial amplitude times the dampening factor times the oscillating part in the z direction, and then that's going to be in the x direction. The magnetic field now is perpendicular to the electric field and the direction of motion. So that means the B field is our velocity, is 1 over the velocity times the amplitude of the electric field, and then everything else is pretty much the same. Now it's if the direction of motion is z and the electric field is polarized in the x direction, the magnetic field is now pointing in the y direction. Okay, so let's rewrite this in complex form, where this constant k is some amplitude, or sorry, it's some real number, capital K, times e to the I, some phase. So basically, we can write it now as a real modulus times a phase angle. So if this was true, then if we write it this way, then capital K is going to be equal to the modulus of k tilde, which is just the square root of the real part and the imaginary part squared, just applying Pythagorean's theorem. And this would be equal to omega epsilon mu square root 1 plus sigma over epsilon omega quantity squared. So it's still kind of a goofy number. It's the square root of a square root, but that's what it is. The phase we can solve as just the inverse tangent of kappa over k. But remember, that's kappa, not the capital letter K. So now let's look at the connection between the magnetic and the electric fields. So the magnetic field amplitude times some phase is equal to capital K times its phase over the frequency, the magnitude of the electric field, e to the I, the complex part of its amplitude, delta E. So essentially what have I done? I'm basically just saying that the amplitude of the magnetic field is equal to the amplitude of the electric field divided by the speed. But I've just written them out now in terms of real and complex parts. Okay. Okay, so now that we've done that, I can look at this equation and try and basically rearrange things. But what we have is the real amplitude B is equal to this real number, capital K, divided by the real number, which is the frequency, times the electric field's amplitude, the real part. And then we have e to the I phi plus the complex part of the electric field amplitude. Now, don't forget, there is a complex part to the magnetic field's amplitude. And so if you equate, you can basically equate the things, the real parts and the complex parts. So that means that the complex part of the B field's amplitude is related to the electric field's components. And so what you get is that this phase in the wave number is related to the complex part of the magnetic and electric fields. Okay, so then what does that even mean? Okay, so we worked this whole thing out, and we went from, we started with the complex amplitudes, we wrote them in this in this basically polar form, the polar form of the complex numbers. And what we find is that we get this phase, which is now is a difference between the complex part of the amplitudes of the magnetic and electric fields. So essentially what that means is that the B field lags behind the E field. Okay. Or, so if I think about it, here is my interface. Here is my conductor right here. We're going to say this is just air or vacuum. And what you have is you have this wave coming at it, which has an electric field, and it has a magnetic field, like so. And when we get into the conductor, it keeps moving forward. You have the electric field, which is now starting to dampen. And you have the magnetic field, which is also starting to dampen, but now it's not in phase with it. So what you'll get is a magnetic field, which is now kind of hard to draw, which is now not in phase. So just to kind of illustrate this a little bit more, instead of trying to draw them transverse like that, what if I was to just draw the electric field like so, and now the magnetic field, and now the magnetic field, whoops, whoops, starting to get out of control here. Let me start again. What you get is the electric field dampening out, magnetic field dampening out, but now out of phase with the electric field. So in the air, the two waves are in phase with each other. They have a maximum at the same time. They have a minimum at the same time. Inside the conductor, now they shift with each other so that they're no longer in phase with each other. So the last thing that we can do is, now that was the complex part, that was the imaginary part, we can relate the amplitudes, because we can now say that B0 is equal to capital K over omega, and that's equal to the electric field's amplitude. So B0 over E, which is essentially now capital K over omega, which, when you put this together, gives you the square root epsilon mu square root 1 plus conductivity over the permittivity, the frequency, that whole thing squared. So again, like I said, you get this kind of weird square root of a square root, but the interesting thing is that it contains the information of the permittivity of the conductor, the permeability of the conductor, so the electric and magnetic properties of the material, and the frequency. So it's frequency dependent. So how these amplitudes are basically related to each other, the relative strengths of their amplitudes depends on the frequency of the light that is now impinging on the conductor.